Hey everyone, and welcome to this explainer. Today we're diving deep into the fascinating underlying rules of conic sections. You know, if you've ever stood under a beautifully curved architectural dome, or maybe wondered how a telescope perfectly focuses light from distant stars, well, you're actually seeing this exact math in action. We're going to unpack the abstract rules of geometry, specifically focusing on the parabola, and we'll break it all down step by step so we can really see how the mathematical engine works underneath.
So here's our roadmap for today. First, the beautiful geometry duality. Second, anatomy of a parabola. Third, standard and shifted parabolas. Fourth, the parametric coordinate system. Fifth, solving parabola puzzles. And finally, number 6, geometry in the real world. Let's get into it.
Section 1. The beautiful geometry duality. There's a really incredible quote from our source material that says, "Unlock the duality of geometry, where points become lines and lines become points." I mean, that sounds a bit like magic, doesn't it? But in higher geometry, this is a very real mathematical phenomenon known as pole-polar theory. We're dealing with a mathematical universe that can quite literally fold in on itself, completely swapping the identities of specific coordinates and linear equations.
Okay, to ground this abstract theory, let's do a quick thought experiment. Picture yourself standing outside a massive, circular building. Now imagine you have 2 laser pointers, and you shine them out so the beams just barely graze the left and right sides of the outer walls. Those 2 specific points where your lasers just touch the building, well, if you were to draw a straight line connecting them, that line actually has a deeply fundamental mathematical relationship with exactly where you are standing right now.
That specific connecting line has a name. It's called the chord of contact. Now, the truly wild geometric insight hidden here is how we actually find the equation for that line. You can literally just use the t substitution rule based on your external coordinates. The crazy part is that you are using the exact same tangent formula you'd use if you were standing directly on the building's wall, even though you are standing way out in the parking lot. It's an absolutely perfect demonstration of that geometric duality.
Moving right along to Section 2, anatomy of a parabola.
So every conic shape is born from one massive general equation. But how does that equation actually know what shape it's supposed to be? Well, it all comes down to a determinant value, which is represented by the Greek letter delta. If delta equals exactly 0, the whole equation just collapses. Bam! You just get a pair of straight lines. But when delta does not equal 0, that's when we get the really beautiful sweeping curves of proper conics, like circles, ellipses, hyperbolas, and of course our main focus for today, the parabola.
Alright, so once we know we have a proper curve, because delta isn't 0, how do we know for absolute sure that we're dealing with a parabola? The algebraic condition is actually beautifully simple. H squared must equal a times b. Think of it like a delicate balancing act. If h squared is greater than ab, it stretches way out into a hyperbola. If it's less, it closes back up into an ellipse. But that perfect, razor-thin balance where h squared equals ab, that right there is a strict, undeniable signature of a parabola.
And we can see exactly why that h squared equals ab rule is absolutely crucial. When you examine the homogeneous terms of the general equation, that's the ax squared plus 2hxy plus by squared part, that specific condition actually forces those terms to cleanly collapse into a perfect square. It's not random at all, it's this highly structured algebraic symmetry that literally dictates the physical shape of the curve. Let's look at Section 3, standard and shifted parabolas.
Okay, let's talk standard orientations. On one hand, we have y squared equals 4ax. This gives us your standard parabola opening up to the right, with its focus sitting comfortably at the coordinates a0. Conversely, if you simply throw a negative sign into the mix to get y squared equals negative 4ax, the entire structure completely flips. It opens to the left, and it pushes that focus over to negative a0.
Now, no matter which way the parabola is facing, there is a golden rule you absolutely must remember. Every single point on a parabola has a focal distance. That's just the distance from that point on the curve to the focus. But the minimum focal distance possible, that is exactly A. And there is literally only one point in the entire mathematical universe where that minimum distance happens, perfectly at the vertex. The moment you move anywhere else on the curve, that distance immediately gets larger.
Now, of course, in the real world, parabolas don't just sit perfectly centered at the origin point of 0, 0. But if we shift the vertex to a completely new location, let's say coordinates alpha and beta, the fundamental curve geometry doesn't change one bit.
All we're doing is modifying our algebraic variables from x and y to x minus alpha and y minus beta. The physical shape is exactly identical. We've essentially just picked it up and moved it somewhere else on the map.
Section 4. The parametric coordinate system.
So let's see how this logic builds across all the standard orientations. Instead of constantly juggling an x and a y, what if we just introduce a single parameter called t? For a standard right-facing parabola, any point can be defined cleanly as a t squared to a t. And when you map it out, you can see how beautifully that logic scales. Facing left, just make the x-coordinate negative. Facing up or down, you just swap the components around. It's kind of like a universal translation key for conic sections.
To truly grasp what this means, let's visualize it. Imagine t is time. As t starts way back at negative infinity, we are way down on the bottom branch of the curve. As time sweeps up towards zero, our point slides along the parabola until it hits the vertex exactly when t is zero. Then, as t grows towards positive infinity, the point traces its way right up the top branch. Just like that, a single flowing variable mathematically draws the entire shape for us.
Section 5. Solving parabola puzzles. Building a non-standard parabola equation completely from scratch means we have to rely on the absolute core definition of the shape itself. You see, a parabola is really just a collection of points that are entirely equidistant from a single dot, which we call the focus, and a single line, the directrix. So the steps to solve any puzzle are straightforward. Identify your focus, identify your directrix line, and then strictly mathematically enforce that the distance from the point to the focus, SP, perfectly equals the distance from the point to the line, PM.
Let's walk through an authentic, step-by-step solution from our source material. We're given a focus of 1, -1, and a directrix line of x plus y minus 7 equals 0. By setting up our SP equals PM distance formula and squaring both sides, we end up with this pretty large algebraic expansion. But check out what happens when we simplify. The first three terms of our final equation, x squared minus 2xy plus y squared, what is that? It's a perfect square, x minus y all squared. Just like we established earlier, those homogeneous terms absolutely must form a perfect square to guarantee we are looking at a true parabola.
And this next example brilliantly illustrates why those parametric coordinates we learned about are so incredibly powerful. This puzzle asks for the area of an equilateral triangle shoved perfectly inside a parabola, with one of its corners touching the vertex. Now, if you try to solve this with standard x and y coordinates, it would be an absolute nightmare. But by assigning the top point of the triangle the parametric coordinates 2t squared 4t, we can just use basic trigonometry, specifically the tangent of 30 degrees, to solve for t almost instantly. We're seamlessly merging pure geometry with curved algebra.
Bringing it all home with Section 6, Geometry in the Real World. So why does any of this actually matter outside of a math class? Because the exact math we just dissected literally structures our modern world. When engineers are designing multi-element optical lenses for high-end cameras or space telescopes, they are actively calculating chords of contact and focal minimums. Architects rely heavily on these exact perfect square equations to analyze stress distribution so that massive curved domes and arches don't just collapse under their own weight. And hey, every time you play a modern video game or watch a CGI movie, the software is constantly using these geometry duality principles to rapidly calculate ray tracing and collision detection.
We've covered a ton of ground today, from the pure duality of points and lines to the parametric sweeps that trace out conic curves. But I really want to leave you with this final thought. If a few abstract mathematical substitutions can magically flip the identity of points and lines and perfectly predict exactly where a laser beam bounces off a circular building, how else is this hidden, elegant geometry secretly structuring the physical space you are sitting in right now? Think about that the next time you look at a curved structure. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.